ladies and gentlemen. I don't really need to introduce Nigel Wright. This is the third time he's lectured to us. But he's had a long career in designing spacecraft and bits of spacecraft. 7 missions have actually flown successfully, and there's an 8th which will go before too long. And he did have some involvement. The reason he's talking to us about Hubble tonight is one of the projects he was involved with is bits of Hubble. So, and I think the only thing that's changed since the last time he spoke to us is you're now, an adjunct lecturer at Bristol.
Honorary lecturer.
Honorary lecturer
in Space Systems and Technology.
Space Systems and
Bristol
Technology. University. Okay, so I think I'll just turn over to Nigel.
Thank you. Let's just check. Yes, I can hear the microphone's working, so that's good. Right, good evening, everyone. It's nice to be back and to be able to have the opportunity to talk about this fantastic spacecraft, which was one of the first ones I worked on all those years ago, and it's now coming up to 36 years it's been in orbit, which is amazing to think. And as I'll mention later on, it was only designed for 15 years with servicing missions from the space shuttle. So the fact that it's still going now is completely unexpected, from where we started. And in fact, this talk, I was preparing a talk at the British Museum as part of a celebration of the 30th anniversary in 2020, when COVID struck and the whole thing was cancelled. So here we are 6 years later, and it's nice to have the opportunity to talk about it and to celebrate this this satellite. So what can you see here? Well, you've got a couple of mission patches on the left-hand side. One that says 35 on it, because they haven't done the 36th one yet. That's still a couple of weeks away. And then in the upper left, you can see, upper right, you can see the telescope as it's being first set to fly from the back of the shuttle cargo bay in April 1990. And below here, this is the operations team at the Space Telescope Operations Center in Goddard Space Flight Center, and I'm there. Here I am under the aperture door in my jacket, which you see here tonight. So let's begin. So the Hubble had a bit of a checkered history, and I'll say something about that on the way through this evening. But it finally got into orbit in April 1990, and there was a team of us in Bristol that were involved in this, and we're very happy to see it fly. Unfortunately, soon after the launch, there was a number of problems identified. In particular, the primary mirror had what we call spherical aberration, which I'll go into a bit more detail later. And this was, a real issue for NASA, because it threw into doubt, do these guys really know what they're doing? This was the government talking to NASA, and they staged, what turned out to be a spectacular repair mission in December 1993. So I'll talk about those details. I'm going to give you a brief history of the telescope, why we've got a telescope in orbit, why that's a good idea at all, a bit of an overview of the Hubble, a bit about the organisation, because this is one of the reasons it took so long, and then I'll home in on the European contributions to the Hubble. And the bit that I was involved in was the solar array, so I'm going to talk a lot about the solar array, so no apologies for that. And then as we come to the launch, well, the first launch was supposed to be in 1986. It didn't happen because the Space Shuttle Challenger blew up several months before the launch of the Hubble was scheduled, and that had a number of impacts on the Space Shuttle program, on a lot of things, but including the Hubble and the solar array as part of that. And then I'll talk about the preparations for the launch and the launch itself. And then I'll look at the primary mirror and what was done to correct that. There are also some solar array disturbances, which is one of my exhibits here. I'll use to talk about that. I'll briefly mention the later servicing missions, and one of the unique things is that the solar arrays, or three out of the 4 wings, came back to Earth and they were analysed on the ground. So it's not often you get a piece of hardware returned from space and the chance to examine it in detail. So I'll talk a little bit about that because that was quite interesting. And then I'll wrap up at the end with something about the HST science and what the future might be for the HST in going forwards. So where did it all begin? Well, there was a chap called Lyman Spitzer, who's this guy in the upper picture, who had the first idea. So he could be considered to be the father of the Hubble Space Telescope. And he had the idea of placing a large telescope above the atmosphere in space in the mid-40s. And he was obviously committed to this, and he carried on, lobbying the science groups, and he led a study of this large space telescope in the 60s, but it wasn't until 1977 that it really took the form that it now has, when NASA approved the budget, and along with that, the contributions from the European Space Agency. And the launch at that time was planned to be in 1983. So the telescope was designed for 15-year life, and the key thing was that it was going to be launched in the space shuttle, and it was going to be serviced in orbit using the space shuttle. And the idea, over 15 years, you could replace some of the old technologies for particularly some of the scientific instruments, things like the batteries, which had a limited life, reaction wheels, things like that, and keep it in good operating state. And it wasn't until partway through the project that it became the Hubble Space Telescope, named after Edwin Hubble, which is the gentleman here smoking a pipe. And Hubble, of course, is the responsible for the Hubble constant and the expansion rate of the universe, as you may know. So why do we want to put a telescope in orbit? Well, there are a lot of advantages in getting above the atmosphere. And what you can see here is a spectrum of wavelength of radiation along the horizontal axis, and absorption from 0 to 100%. So you can see in the wavelength region, sort of 0.1, 0.2 microns, which is in the ultraviolet, virtually nothing gets to the ground for a ground telescope. It's all absorbed by the atmosphere. Whereas in the visible, most of the light will get to the ground, particularly in the blue end. So the 2 green arrows at the top are the wavelength range that the Hubble is operating in. So it's from the sort of hard ultraviolet out to just into the infrared at around 2.5 microns. James Webb, by comparison, which is sometimes viewed as the successor of the Hubble, is much more in the infrared. So it's about 0.6, so it's about here, all the way off the page, that way, out to 28 microns. So it's a completely different beast and accesses different science. The other reason you want to get away from the atmosphere is the atmospheric turbulence. So this makes the images blurred, and that is the reason why stars twinkle. Not because they're happy, it's atmospheric turbulence. So what does the Hubble consist of? Well, it's this large thing, and I'll talk about the size of it in a minute. But you can see it's basically a tube, so it looks like a telescope. It's got an aperture door at one end, and it's got these 2 large solar arrays sticking out the side. And the solar array was one of the European contributions. The other contribution, in the back of the telescope here, you can see 4 segments, and these are the axial scientific instruments. And one of those was the faint object camera, which was the European instrument. And inside that was something called the photon detector assembly, which was something that was also done by engineers in Bristol at British Aerospace. So I'll talk a little bit about that later. These axial instruments, to give you an idea of scale, are about the size of a telephone kiosk. So they're quite big things, and they weigh about half a ton. So here's the telescope in its clean room prior to launch. You can see 2 solar arrays rolled up on the side of the body, the barrel of the telescope here, on each side. And one of the things that's going to be apparent in a moment when I show you the next slide is it's really fills up the cargo bay completely of the space shuttle. It's, it occupies as much space as it can. So in fact, the original primary mirror for the telescope was bigger, but when the space shuttle was being redesigned and constrained and the size of the cargo bay was shrinking a bit, they had to come down from about 3-meter mirror to about 2.4 meters. So this was, purpose built for the space shuttle. And as you can imagine, the design for the solar array was severely constrained by this volume, by this limited volume that we had available. And the other thing I'd like to point out on here is this European part of it. You can see the NASA logo here, and you'll see a little ESA logo at the side. And this is reflecting the fact that it was 85% US, 15% European. So the proportions of the logo go with that as well. Right, here's an image, not a real image, but you can see a drawing or with the telescope in the cargo bay, and you can see what I'm saying. It's really, it couldn't be any bigger. So the body of the telescope is about 13 meters in length, from top to bottom, and it's about, in the widest part, it's about 4.3 meters in diameter. So it's about the size of a sort of single-decker bus, that sort of size. 11 tons at when it was launched, and the primary mirror is 2.4 meters. That gives you a rough idea. Right, horrible diagram. This is really just to show how many different NASA centers were involved. Eventually, Marshall Space Flight Center in Huntsville, Alabama, were appointed as the overall lead center for the project, but at the beginning it was more chaotic, shall we say. There was also Goddard Space Flight Center involved in Maryland, and they were responsible for the operations, for the scientific instruments, and the mission operation planning, all of that sort of side of it. You had Johnson Space Flight Center for the crew, because of course it was a space shuttle launch. They had astronauts servicing the telescope. You had Kennedy Space Center for the launch. So you had 4 NASA centers involved. And then there was the scientists had their own Space Telescope Sciences Institute. And then, you come to industry. So we had Lockheed, who were responsible for a major part of the telescope. Perkin-Elmer were responsible for the optics, primarily. And the Europeans, of course, had the responsibility for the solar arrays and the faint object camera. So this is one of the reasons it overran in terms of time and money, of course. Was the organization wasn't very good to begin with. And this was, it improved after Marshall were put in charge, and people got used to working and were less bothered about the politics. But, this didn't set off in the optimum way, shall we say. So the European involvement was led by the European space agencies. You'd expect there was if you like, an interagency agreement at top level between ESA and NASA of what would be provided. And the deal that was cut between the two was that Europe would provide 15% of the funding in terms of these contributions, the solar array and the faint object camera, and in return, European astronomers would get 15% of the viewing time. That was the idea, and that was 80 million euros in 1976. Obviously, a lot more these days, but just to give you an idea. As it turned out, European astronomers had by far more great ideas, and they exceeded the 15% viewing time just based on scientific merit, and that their ideas were justified. So Europe got a good deal out of this. A few words on the photon detector assembly. This was also something that was developed by British Aerospace in Bristol with the support of University College London, and it's really the heart of the faint object camera. And what it's doing is it's basically a big photomultiplier or an image intensifier. You get a photon arriving from a distant star or galaxy. It goes through an image intensifier. I think there was something like 30 kilovolts, high voltage on this system, and that when the photon struck a target, it generated electrons, which were then accelerated, and there was a number of stages. So you ended up with a decent sized signal from one photon. But it's essentially almost counting individual photons, hence the name faint object camera. And here we are. It's capable of detecting a candle from 40,000 kilometers, which 40,000 kilometers, because we've got Artemis flying at the moment, that's a tenth of the way to the moon. So you can imagine, someone out there with a candle, you'd be able to see it. The solar array. So I'm going to talk about the solar array now and some of the details of it. We've already talked about the limited volume you've got. That it's got, when it's stowed for launch, it's got to occupy very little space, and this led to a complicated deployment system for the solar array, which not only was motorized, but it also had to be capable of being powered by the astronauts using their power tools, if that proved to be necessary, because it was critical. If you've got no power from the solar arrays, you've got a dead telescope after a while. So that was one of the big features. The solar array drive. The solar arrays are rotated towards the sun, so for optimum generation of power. And this solar array drive had to operate with very low torque noise because of the precise pointing nature of the telescope. With the deployment, the solar cell blankets had to be capable of being furled and unfurled. The idea was it would be furled up when you approached a servicing mission. The idea was that it would have to be furled up, and then if you wanted to replace the solar arrays, you'd have to do that step. So they were designed to be not just deployed but also retracted. The electronics that goes to control all of those was part of the solar array system, and the adapter interface. So this is at the root of the solar array, where it's attached to the body of the telescope. That had to allow for a physical separation, so the astronauts could remove it and put it back in the shuttle, pick up a new solar array and fit it. So this was one of the interesting features from a design engineer point of view. You don't normally have to worry about astronauts handling your equipment, but we did. So this picture is of stowed solar array. So this is it. You saw it sort of stored on the side. So the body of the telescope is underneath here, and you can see it's attached here. This is the adapter interface that I've just mentioned, and then it's got two latches which are powered and can be released, so you can swing it away from the side. Now the dimensions are in inches for those of you with sharp eyesight, but we can ignore that. It was in inches, of course, because it was US. In Europe, we were all in millimeters and so on by then. So this is a picture of the deployment sequence. So you can see here in the upper left-hand side, the first deployment, the primary deployment, is moving the arm away from the body of the telescope, a simple 90-degree movement away. And then the secondary deployment is the unrolling of the solar cell blankets off this central drum in both directions. And you can see that's what's actually happening here on this photograph. So this is a photograph in the clean room at Bristol during a secondary deployment test. You can see the blanket coming off the drum. It's part way out at the moment. And you can see these white polystyrene floats underneath it. And this is because it's floating on a water table. There are 2 water tables, one for each blanket. And this is to simulate the zero gravity or microgravity in space, so that the motors see a reasonable, realistic resistance to deployment. The tip-to-tip distance on the solar array when it's deployed is about 12 meters, and you can see the size of the people here, so you get an idea of the scale of it. And it's about 2.4 meters across there, so about 8 feet. So we talked about the EVA features, the extravehicular activities. This is the astronaut features. In the picture here, you can see a training activity, handling one of the solar arrays. It's not a real one, it's a dummy. It's in a water tank. Again, this is to simulate neutral buoyancy, so, as if the astronauts are floating in space. And they're rehearsing activities that they'll need to do in orbit in the next servicing mission. So this is a huge, this neutral buoyancy facility at Johnson Space Center is a huge water tank or swimming pool. And this was the focus of a number of rehearsals leading up to each servicing mission. And one of the things it really showed and demonstrated was the value of having the design engineers participate in these tests. I mean, not for the solar array from Europe, but obviously for the scientific instruments, it would be from the scientific instrument camps. So let's arrive at 1986. We've got the Challenger, which unfortunately exploded just after liftoff in January, and was a surprise, I think, for many people in the industry and associated with it at the time. The HST launch was only some months away then. I think it was about 6 months later. So, of course, the shuttle flights ended up being suspended for a few years, and the telescope was put into storage or put back in its clean room, and the solar arrays were removed and sent back to Europe. And, after some discussion, they said, well, we'd like you to undertake some modifications to the solar array. So what did this consist of? Well, the main thing was to increase the power from the solar array, and this was done by changing the solar cell blankets. So we had a more powerful solar cell, still silicon, but it was a much more efficient solar cell. And the other things that were done was atomic oxygen had been identified from the earlier space shuttle flights, because you had the space shuttle would fly for a week or a couple of weeks, come back down to Earth, and then you'd have people crawling all over it. And they began to notice that there was some damage, and it was eventually traced to being in atomic oxygen, which is prevalent in low Earth altitudes, and I'll show you a picture in a moment. And of course, for the solar array, it was on the outside of the satellite. It had to be, so it was very vulnerable to atomic oxygen attack. So we had to undertake a number of things to reduce that vulnerability in terms of coatings and so on. Another thing that was done was the fracture control. The space shuttle said we've got some safety recommendations coming out and from the post-Challenger era, and we want you to, scrutinize your design to make sure that there's no danger of cracks growing and propagating and endangering the shuttle during the launch. And this was the first time this had to be done on a European spacecraft. It wasn't something that was done regularly or done at all prior to this. Similarly, atomic oxygen wasn't done. This was the first time it was actually done on a European project. And then they had a load of other ideas to do with the astronaut handling of the hardware. Where can we put some handlebars on these things? This sort of conversation. So atomic oxygen. What you can see on this diagram is a density on a logarithmic scale on the bottom, and then altitude in hundreds of kilometers going up the side. And there's a red line at 400 kilometers for reference purposes. I mean, the Hubble altitude is between 600 and 400. And you can see the most numerous species at that altitude is atomic oxygen, which is, as you might imagine, very reactive and will chomp anything it can possibly do. So let's have a look at the solar cell blanket. What does it consist of? Well, you've got your cell in the middle, which is the blue bit, which is about 1/4 of a micron thick. Sorry, 1/4 of a millimeter thick. So it's, you can easily hold this and just crack a cell very easily. They're very fragile. And then you've got various layers. You've got the important ones are you've got a cover glass on top, which stops some of the ultraviolet getting onto the cell and damaging the cell, reducing the power over time. And you've got a substrate on the back to support it mechanically. So you've got glass fiber. You've got also a silver mesh because you've got a electrical circuit. So you've got to have the current be able to flow back through the silver mesh to complete a circuit. And then not shown on here are the interconnects. So you have the top of one cell connected to the bottom of the next one in a chain like this to create the circuit. So the total thickness of this assembly was 0.7 millimeters. So it's incredibly thin, and this is why it's a flexible blanket and can be rolled up. So what are we doing here? Well, we've got another water table you can see in the foreground, and then we've got a gantry with 3 astronauts on it and myself. And what we're doing, we're actually trying to get the astronauts the view they would have from the back of the shuttle cargo bay, looking at the solar array as it's deployed. And this is the sort of image you can see in the top right. That's taken from the same place. You're looking towards the back of the shuttle cargo bay. You've got the telescope up here. It's not attached to the robot arm, but it would be when the solar rays were coming out. So this was to give them an idea of what they could see, what visual cues they could see during the deployment test. So they came to Bristol for about 3 or 4 days, about a year before the launch. Of course, once the solar array's been deployed, they want to come down and have a closer look. And here we've got Charlie Bolden and Bruce McCandless with me, and they're interested in one feature of the solar array here at the end of the boom. This is one of the booms I've got here, but I'll talk a bit about more of those later. Charlie was the pilot, and he went on to be the 10 years later, he was the boss of NASA, the NASA administrator. And Bruce was older than Charlie. I think he was in the 3rd or 4th astronaut recruitment corps. And he was the guy in 1984 who flew on the manned manoeuvring unit. But they were both very impressive engineers, very wide knowledge. And here we are for a group shot in front of one of the solar arrays. This is one of the ones that was launched with the telescope in 1990. So you get, again, this is a stowed solar array. You can see what the size is, roughly. So let's come to the launch in April 1990. It was mission STS-31, it was known as, on Discovery. It was launched from Kennedy Space Center, and the control center was at Goddard. For the telescope, the control center was at Goddard Space Flight Center. The shuttle control center was in Houston at Johnson. One of the things I mentioned is, and it's probably obvious, the solar array has to be deployed in a certain time scale. If you can imagine, the telescope is connected by the batteries are all charged on the ground before launch. It's plugged in via umbilical connections to the space shuttle, but at some point you have to disconnect that and then position the telescope ready to deploy all its appendages, including the solar arrays, and then set it to fly. And there was about a 6-hour window when the umbilicals were disconnected, batteries would start to drain, and the solar array had to be out in that time. So we had a lot of attention in our part of the control room. And unfortunately, with one of the wings, we had a problem with the telemetry from the blanket tension monitoring system. And this was reporting high tension, and the motors, the electronics was detecting this on board and cutting the power because it sensed there was something preventing it from unrolling. There was lots of scrutinizing of the images in orbit. And eventually this was disabled. This telemetry was disabled because it was considered the sensor was faulty and was probably open circuit or whatever. So as this was going on, which this obviously took some time, half an hour or so, the crew were suiting up, ready to go outside in case they needed to wind it out manually. And they were in the airlock before they got the call that they could be stood down. So it's a close thing, but the solar array did deploy in the intended way. So we come to the story of the primary mirror, which was very disappointing and gut-wrenching thing to hear about. Although we didn't have a part to play in the primary mirror, of course, in Europe, but this was discovered within the first few weeks following the launch. The first images came in. There was this blurring and halo, and it was pretty obvious to some of the astronomers. Well, that looks like spherical aberration. What's going on? And the primary mirror was too flat, precisely by 2 microns. So 2 microns doesn't sound very much, but at optical wavelengths, of course, that's a number of wavelengths, and it was obvious in terms of the performance. So this was eventually traced to, after an inquiry, to some of the calibration equipment used in the mirror manufacture that was set up incorrectly, and that was the result. So NASA were faced with this almighty situation with egg on their face, and what can we do about it? So things quickly moved to, well, that's where we are and how we got here, but what can we do about it? So the answer, of course, was to fit a pair of spectacles to the Hubble. And this is in crude terms, and this is what the corrective optics Space Telescope axial replacement COSTAR became. And it was developed really very quickly for a space program, just over 2 years. And this basically sat in place of one of those telephone kiosks in the back of the telescope. and deployed some optics out the front that was able to interrupt the beam onto the other instruments and correct them. So, as simple as that. Right, the other thing that became apparent was because the telescope's in low Earth orbit, it's going in and out of, it's orbiting about 15 times a day, every 100 minutes. And it's going in and out of eclipse. It spends about 35 minutes in eclipse, in the shadow, and then it's moving into the sunlight part, which is about 65 minutes. And as it was going in and out over these periods, the temperature of the array was changing significantly. You know, the solar cell blanket temperature would go from maybe plus 100 in full centigrade in full sunlight to minus 100. So this is a tremendous change, which for the blanket wasn't a problem in terms of the materials on it. But this blanket was pushed out by two of these bi-stem booms, which are these tubes you can see here. And these tubes were, you know, 6 meters long either side. And they were responsible for causing this jitter. In the short term, the telescope control system was able to be modified from the ground and try and allow for this so that the telescope recovered as quickly as it could during these events that lasted some minutes. But it became obvious that for the second set of solar arrays, and the repair mission was now being framed in '93. So for the second set of solar arrays, we had to have some way of mitigating this problem or eliminating it even. And what's at the origin of this is you can see in cross section here two sort of C sections of boom, and there's an opening, and the opening is because they end up being rolled flat on a cassette, and they come out in this sort of fully formed boom section out of this mechanism at the end of it, at the end of each end of the drum. So it was a consequence of the design of these bi-stem booms, and what was happening is you've got one side in the sunlight, of course, and one side facing away from the sun. So there's a temperature gradient across these, and these booms were rotating inside each other, and that wasn't without friction. So it would stick and then move, and that was what was causing the jittering. So the solution was, and you can see it here, was to fit this concertina around the boom, which could collapse for when it was stowed, and then as the boom deployed, it got pulled out. And this limited the temperature difference in the boom. Here you can see a little graph, and it goes from, instead of being from sort of 25 degrees down to, well, below 5. So, you know, at nearly 25-degree temperature difference, it goes down to about 2 or 3 degrees because it's inside that shield. So this was the fix that was implemented on the second set of solar arrays, which fixed the problem. Right, so the repair mission, the main focus of the repair mission in December '93 was, of course, the primary mirror. But the second set of solar arrays were also part of that, and the solar array was replaced. Now, unfortunately, one of the wings had problems retracting to do with the damage from these booms rotating. And the astronaut, Catherine Thornton, who's here sitting or standing on the end of she's standing on the end of the robot arm attached to the shuttle, and she's holding one of the solar arrays, and she had to let it, she pushed it off. She didn't bring it back to Earth. I don't know. The other wing came back to Earth, and I'll talk about what we did with that in a moment. Some wag in mission control, I think he was, did this cartoon of a fluttering solar array being pursued by a pterodactyl with some amorous intent. The reality was, as the array was pushed away and the shuttle and telescope backed away from it, and it burns up in the atmosphere eventually, because of the thrusters from the shuttle, it was fluttering because these thrusters were impinging on the blanket and making it as if it was flying. So that's what prompted the cartoon. To mention the other servicing missions briefly, the main one that involved the solar array and the faint object camera was SM3B in March 2002. So at this servicing mission, the faint object camera was removed. So it had flown, since April 1990 to March 2002. So for 12 years. The solar array was replaced at this point. The European second set of solar arrays was degrading over time due to radiation damage, so producing less power. So this was always going to be the case. This day would come. NASA decided to fit some ugly, short, stubby wings, as you can see in the photograph, not the beautiful long solar arrays that we've got from Europe. These are short and stubby because they're using gallium arsenide rather than silicon, so they need a lot less area to generate even more power, not even the same power. And these are the ones that are still fitted to it today, providing enough power for the telescope's needs. At the bottom of them, though, is a European solar array drive and the electronics to rotate it. So there's still a bit of European hardware on there. So that was in 2002. There was some other servicing missions, mainly to do with instruments and reaction wheels. The last one was in May 2009. And since then, the telescope's been untended by shuttles and man, and it's been on its own. So, that's 17 years now. It's had the odd hiccup, but it's always been able to recover from them. So the solar array systems, the first one flew for over 3 years, and the second one flew for over 8 years. And one wing from the first solar array came back to Earth. Both of the second ones did. I've got 2 of the solar cells from the first wing that came back. There were about 24,000 cells on a wing. These were some of the less interesting cells because they didn't have any micrometeorite impact on them. But these were mounted and presented to the team, which is a nice thing to have. So you can see how big the solar cell is. It's about 4 centimeters by 2 centimeters. So that it could be rolled up on the drum, of course. So let's this just to show you a quick picture of Service Mission 3B. So you can see telescope in the background with the old solar array still on there, and these are the 2 replacement solar arrays that were going to be fitted, with the astronauts starting to remove them. You can see these white handlebars fitted on these ones. So what can we say about the solar array wings that came back? Well, as I said earlier, the first thing to remark on is that this was, an unusual opportunity, should we say, or unique opportunity. Because hardware rarely comes back to Earth. If it does, it's usually burning up in the atmosphere somewhere. It's not landing in a controlled way and heading off to a laboratory to be investigated. So both solar arrays were, or 1.5 solar arrays came back. They measured the performance of the solar cells, and the degradation was much less than had been expected. And we'd obviously allowed various factors in the budgeting for how much power we'd lose due to micrometeorite damage, radiation damage, etc. It provided information on micrometeoroid fluxes in low Earth orbit, and you can see a solar cell below here with a nice ding in it. It showed that the atomic oxygen protection had worked well. One of these solar arrays had been in orbit for 8 years, so it had 8 years of atomic oxygen attack. And going in and out of eclipse every 100 minutes, that's accumulating in 5 years, I think it was 30,000 thermal cycles. So there's a lot of thermal cycling, which in some areas showed, Teflon you wouldn't think would be that bad, sort of plasticky material, but that was showing signs of damage from thermal cycling. One of the most interesting things for me was they did some chemical analysis of these impact craters to discover what was in there chemically. And, from dust, you'd expect, well, we're going to find some silicates in there. Well, they did find some of that, but they also found aluminium and sodium. And this was put down to being from the exhaust of rocket motors. And things have only got worse since then with the amount of launches. So in low Earth orbit, there's a lot of exhausts from rocket motors with solid particles existing, not atoms and molecules, but, solid bits that are potentially damaging your low Earth orbiting satellite. Right, I'm coming towards the end, so I'm going to talk a little for the next few minutes about some of the science achievements of the Hubble. One of the things was the measurement of the Hubble constant, no surprise there, or to a better accuracy. The universe expansion rate, and not only is it expanding, but it's also expanding at an ever increasing rate, which was a bit of an unusual discovery at the time. And cosmologists are still not struggling to explain it, but this is what's given rise to dark matter and bits we can't see that are the explanation behind it. For me, one of the interesting pictures was the Hubble Deep Field, where you stare at the part of the sky which looks dark, nothing in that part of the sky, for days, integrate the signals, and you can see some distant galaxies come out of the background, and these are very far away, just on the limit of observation with the Hubble. The births of stars within dust clouds, and I'll show you a picture of the Eagle Nebula in a moment. The fact that most of the galaxies have at their centers a massive black hole. This was another discovery. And then turning to our own solar system, the telescope was used to look at the other planets, and in particular the weather on Jupiter and the other outer planets that have got atmospheres. Exoplanets, these are extrasolar planets, so planets around other stars. The Hubble made the first measurement of the atmosphere of one of these exoplanets. They've now discovered thousands of exoplanets over time with other telescopes as well. But this was the first one that was measured. And this one is about 159 light years away, so not too far away, but a long way for us. And it had the atmosphere was detected to have hydrogen, water, methane, oxygen, carbon monoxide, bit of sodium. So not things that were completely uncommon. This exoplanet is called Osiris, and it's a hot Jupiter type of exoplanet. It's got a similar mass to Jupiter. It's about 3/4 of a Jupiter mass, but it's orbiting the star very, very closely. It's very tight on its star, which is why it was able to be detected in the first place. And it's orbiting in 3.5 days, so it's really whizzing round compared to Mercury or the Earth. And like our moon, it's the planet is tidally locked to the star, so it's always got one face facing the star. So it's got a very hot side and a very cold side. So quite an unusual planetary environment. So this is the photograph of the Eagle Nebula. Probably most of you have seen this one, with the stellar nurseries in these limbs. One of the iconic photos. This is the Hubble Deep Field. So this is taken over a 10-day period. I think there were about 342 exposures, and the size of this image is about the same angular size as a 1/12 of the moon, or a tennis ball at 100 meters is another way of thinking about it. So it's quite a small part of the sky. But when what looked completely empty of features, after that period of integrating the signal, you can see something like 3,000 galaxies, I think, in that image, which is a bit staggering, I think. So people ask me, well, is the Hubble still relevant today? It's been in orbit for 36 years, for God's sake. We've got James Webb. Why do we need this thing now? Well, I looked at the number of peer-reviewed scientific papers as an indicator to see how much science is it generating, and this is a histogram of years going along the bottom and a number of scientific papers, and it's up at around 1,000 papers a year at the moment. And you can see it may not be climbing so much anymore, probably still climbing over the last 10 years, but it's certainly not going down. So I think that answers the question for me. It's still generating good science. Yeah.
In spite of no servicing or anything.
Well, yeah, but the data is communicated down to the ground by radio link. Yeah. So that's the answer to that question. So my last slide is, what's the future? So currently the Hubble's at about 480 kilometers. With the last servicing mission, it was nudged up to around 600. So it's been gradually reducing just because of the atmospheric drag. Although 600 kilometers, there's not much atmosphere there, but it's thin, and the telescope is a big enough body that it will feel it. It will slow down over time. So at the moment, we'd expect atmospheric re-entry probably to be delayed until the mid-2030s, when it gets low enough, maybe starts 300 kilometers, below 300. So it's going to, all things being well, it's going to continue to operate for some years. Obviously, it needs to be funded to be operated in terms of teams on the ground to look after it and operate it. It needs to continue to survive without any significant failures on board. It's got 5 scientific instruments on board, so even if one of them went completely dead, it would still be useful to operate it. But there would be things that would affect all scientific instruments. So a loss of pointing would be, failure in the control system would be a problem. So what's the plan? Well, NASA are studying a couple of plans at the moment, and they essentially revolve around attaching a propulsion module to the bottom of the telescope. And this would be a robotic mission. There wouldn't be any astronauts or anyone involved like that. It would be a spacecraft that would fly up with a propulsion module and some means of attaching it to the bottom of the telescope. And then they would use that propulsion module to either lower the orbit in a controlled way, so it would have a burn up in the atmosphere and plunge into a remote part of the ocean, or they would raise the orbit to 700-800 kilometers, and the telescope would happily sit there for decades until the next generation or the next generation after that had to worry about it. So that's the current status of it, and it's been a very interesting project to work on and follow. and I hope you've enjoyed the talk. Thank you.
I'm sure there are two questions.
Yes, I'm very happy to answer the questions.
Start with this one here.
I think,
Other unit.
I think there's a bit of frustration now at not being able to service it in terms of, say, adding computer capability and such like. Because
Yeah.
when they last serviced it, I don't think computers could do very much. But they can do an awful, in terms of memory, for instance.
Yeah, and to be honest, the space industry lags behind what's happening on the ground in terms of computer chips, because you've got radiation up there to worry about, which we don't have on the ground. So the chips, integrated circuits have to be developed and tested to a much more stringent environment. So they are usually years, maybe several years
You
behind.
still can't take them up there.
You can't take them up there today, but they did take them up there in 2009. I'm not sure when the computer was last changed, but certainly the last servicing mission was in 2009. So yes, since then, nothing's changed on board.
There's a question over there.
Could you just explain a bit more about the atomic oxygen? I'm ignorant enough not to understand what that actually refers to.
Okay, so this is where you've got an oxygen molecule consists of two atoms which are bound together. So in this part of the atmosphere, those are separated by when ultraviolet light hits them. They can separate, and you have two free atoms then. And this is a very reactive atom in terms of chemically, reactive. So if it bumps into a bit of aluminium, it'll attach itself to that, form aluminium oxide. That's what I mean, chemically reactive.
You said that James Webb Telescope is using a very different part of the electromagnetic spectrum.
Yeah.
Well, what's the driver for making it so different?
I could tell you that.
It's an astronomer question.
Oh, right, okay.
It's because
The
James
infrared.
Webb is primarily intended to do research on very distant objects in the universe, which are so far away that, stars like the sun appear redshifted into the infrared. So all the light coming from that distance of the ordinary stars there is shifted into the far infrared. So that's it. That was its primary design purpose.
Thank you very much.
Right. Any more questions?
Yes.
Yeah.
Yeah. You mentioned about the solar array being protected against the atomic oxygen.
Yes.
But I may have missed it. What change did you do to affect that?
Yeah. Okay. Some of the solar cell and the cover glass on top of it weren't susceptible, but the key thing that was the interconnect, which is a metal interconnect running between the top of one cell and the bottom of the next cell, and this was made of silver, and silver is very susceptible to atomic oxygen attack. So we had a couple of design options we were looking at. One was to put a layer of gold on the outside of the silver. That didn't survive the thermal cycling and produced cracks in the gold, and then the oxygen found a way in through the cracks. So that didn't turn out to be the answer. The answer we went for in the end, and the one that flew, was to use molybdenum with silver on the with a silver coating, primarily so that it could be welded at the ends to the silicon cell and the bottom of the other silicon cell, and then there'd be some silver in the middle, which would be exposed, but that would disappear over time. But the molybdenum wouldn't be attacked, wasn't reacted by.
A practical question. You mentioned at the outset that they were working in inches and you were working in metric. How did you overcome that? Because there have been cases where that didn't go well.
Not easy.
Well, we had to work in inches.
Right, so all of the arrays
On
were
the-
in inches.
Yeah, but for the dimensions that were to do with the interface to the telescope. Yeah, so our drawings carried inches. Between us and our European contractors we were working with, we were working in good old millimeters.
Meticulously.
Yeah,
Are they still working in inches with this, the one that's going on?
I think they
The
are.
Americans
yeah.
still working.
The Americans are still stuck in the imperial era, yeah. In more ways than one.
How does the telescope orientate itself in space?
Yeah.
Have little thrusters or something?
Yeah, that's a very good question. It doesn't have thrusters, and the reason it doesn't have thrusters are the ones you might expect, because you end up having your thruster combustion products ending up on cold optics, which isn't a good thing. So because it's in low Earth orbit, it has reaction wheels, which you can use to turn the body. But eventually, what happens, because of the Earth and the Moon, and the Sun, the Moon and the Sun, it accumulates momentum, and the wheels eventually move towards the end of their operating range. So this is a common problem for all spacecraft, and what you normally have to do is desaturate the wheels, offload momentum, and you normally do that with thrusters. So you fire a thruster, and you can slow the wheel down at the same time and bring it back into its normal operating range. So with a telescope, we couldn't do that, but we've got something called magnetorquers, which we're in a low Earth orbit, so we've got the Earth's magnetic field available, and what you do is you change the current flowing through a wire wrapped around this magnetorquer, and that exerts a moment coupled with the Earth's field, and that's what you use.
Interesting science.
Yeah.
Has any of the technology that was developed for this been applied down here on Earth?
I mean, generally the space program, yes. I can't think of anything to do with the solar array.
But one thing which came out with James Webb is there was a lot of not very visible interaction with spy satellite optics.
Yeah, a few people have asked me that one, but I know nothing. So I think some of the NASA engineers knew a lot,
Yeah.
but they were keeping stum on that one.
Well, they said when they said we would really like to have one of these unfolding mirrors, and apparently
Yes.
engineers from the contractor said that we can do that. Was that another question? Any more questions?
Recently, there were complaints from astronomers that a spacecraft coming back, burning up in the atmosphere, were leaving a trail of metals, which lasted quite a while in the upper atmosphere. Is that something you have to take into account, or have to take into account?
Well, the rules have changed over the last 40 years. You're supposed to be very careful now about disposing of your satellite at the end of its life, believe it or not. So whenever we design something now, we have to design for how's it going to be disposed of at the end of its life. And that's normally a matter of having enough fuel on board that you can positively bring it down into the atmosphere and have a controlled burn up and descent into the ocean. The South Atlantic's very popular as a destination. So I don't know the circumstances of that particular one, whether it was an accident and something went wrong and the satellite ended up flying.
No, apparently it was a deliberate burn up where something was returned to Earth, and it left trails of titanium and various other metals in the upper atmosphere.
Ready to hit your next solar cell. Yeah.
Yes.
Yes. I mean, and this is a concern with the increased frequency of launches, of course. With Mr. Musk and his fleet.
There will be more of it.
Exactly. But even he is supposed to abide by these rules. Although Mr. Trump doesn't do that very well.
Anyway, I think thanks very much, Nigel. That really
Okay.
is good.
Okay. Thank you.